Acid-Base Titration Lab by Henna and Cady. The purpose of this lab is to determine the unknown concentrations, the pH, and the pOH of 3 different acids by titration.
Titration is a method used for determining concentrations of substances by adding chemicals of known volume and concentration to produce a reaction. Volume, molarity, and average amounts of substances are used in order to find concentrations. Reactions are shown by a change of color in an indicator. In this case, phenolphthalein was used. Indicators are compounds that change color in response to pH levels. The indicator changes color during titration at the end point. When the acid and base used in titration are chemically equivalent in amount, it is known as the equivalence point. Neutralization reactions are also present in titration. Neutralization occurs when the ions and acids and the bases react to form a salt.
Safety goggles, aprons, gloves, and closed-toed shoes were worn during this lab activity. Students were supervised at all times.
In order to complete acid-base titration, 2 burettes were cleaned, 1 for acid and 1 for base. They were set up and labeled next to each other. The burettes were determined which was to be used for acid and which was to be used for base. The first burette was rinsed 3 times with the acid to be used, and the second burette was rinsed 3 times with the base to be used. The first burette was filled over the 0 milliliter mark with the acid concentration. Some acid was allowed to be released from the burette in order to get rid of air bubbles and reduce the volume to the calibrated mark. Some of the base was allowed to be released to remove air bubbles and lower the volume to the calibration point. The Erlenmeyer flask was placed under the base burette. The contents of the flask were swirled in order to produce a pink coloring.
"12 milliliters of the acid was allowed to flow into the Erlenmeyer flask. The initial recorded volume was then subtracted from the final reading. The difference was the exact volume of acid released and was recorded to the nearest 100th milliliter. 3 drops of phenolphthalein was then added to the flask with acid. The other burette was then filled with the base solution above the calibration point. The concentration of the base was already known. The equivalence had been reached when a light pink color remained after 30 seconds of swirling. The initial volume of the base was then subtracted from the final reading and rounded to the nearest 100th milliliter. These are the charts of data from acids A, B, and C that show the pH, pOH, average molarity, and average number of moles used for all the acids.
After subtracting the final base volume from the initial base volume, you're able to calculate the average number of moles used of the base. Using this, you can calculate the average number of moles used of the acid by multiplying this by the mole ratio, which is 1:1, which can then be plugged into the mole ratio, which is number of moles of solute over liters of solution.
For acid B, the molarity was 5.83 times 10 to the negative second, which was found by multiplying the average number of moles used in the base by the mole ratio and then dividing by 0.012, the number of liters used.
For acid C, the same steps were taken, except when finding the average number of moles used for the acid, you multiply it by 1/2 instead because the mole ratio is different. This is a chart of other groups' data for acid A, B, and C. For acid A, our average molarity was slightly higher than the other groups. For acid C, our average molarity was also slightly higher, and for acid B, our molarity was quite similar. The reason some of our results may have been slightly different than other groups is because of personal errors, including incorrect reading of measurements or not completely cleaning out the burette.